Hello, my dear students. Today's class we will discuss how to draw SFT and BMD for a simply supported beam when it is subjected to a uniformly distributed load. Okay, let us consider a simply supported beam AB of length L. Okay, and carrying a uniformly distributed load of W per unit length as shown in the figure. You can see here this is a beam, simply supported beam AB of length L. Okay, and here UDL is acting here for the whole length. Okay, that is W per unit length. Always UDL is represented by intensity, that is W per unit length. Okay, uh, then we have to convert into load. How? Multiplied by the distance. Okay, now what we will do, let us consider first step is you have to find the reactions RA and RB. Since the load is uniformly distributed over the entire length of the beam, therefore the reaction at the support. How you can find the reaction at the support? Here actually this load, how it is W into L, right? W into L, that is divided by 2, because equally the two reactions that shares that load, right? So WL divided by 2, that is equal to RA and RB. Okay, or 0.5 WL, or you can you can find this shear force, reactions using the conditions of equilibrium. How you can find that? Summation of vertical forces is equal to 0. So what are the vertical forces now here? Both reactions RA and RB both are in upward direction. So RA plus and RB also plus and minus this W. This is acting in the downward direction. Okay, this always acts like this, downward direction. So W into L, uniformly distributed load, you have to multiply by the length, distance. Okay, so that is W into L. Okay, so minus downward direction minus WL is equal to 0. Now then find use another conditions of equilibrium. What is that? Summation of M is equal to 0. So moment is equal to 0. I'll consider about A, moment about A. So I'll write summation of moment about A is equal to 0. What is that now? Here this is RB and this is RA, right? So what is how to find the reaction moment about A? Minus RB, because it is moving like this direction, anti-clockwise direction, minus RB into L, full length. Okay, about A, minus RB into L, then plus minus RB into L, then this load is acting here, W into L into L divided by 2. This is moment. Moment is equal to force into perpendicular distance, right? So here this is intensity, UDL, W per unit length. So that perpendicular distance you have to take, W into L into half of the distance you have to take. Okay, because in this uniformly distributed load the center of gravity acts at the center, so you have to consider L by 2. So plus W at clockwise direction into L, that is distance, into half of the distance. Okay, L by 2 is equal to 0. Simplify this, what you will get? RB is equal to WL square divided by 2, right? Divided by L. Okay, L get cancelled. You get RB is equal to WL divided by 2. That's why once if you get RB, you can substitute in this equation RA. RA is equal to what? Minus this, consider this side, that take it to the right side. So plus WL minus RB. RB is again WL by 2. So RA also you get WL by 2. Okay. So RA is also equal to RB. Both are same. This is also equal to same. This WL divided by 2. Okay. Now reactions are calculated. Next step is you have to find what are the shear force values. Okay. Now then find at different points. Okay. Now what you can do, no, I consider here a simply supported beam. Okay. Simply supported beam AB. Simply supported beam AB and of length L. Okay, total length is L and it is uniformly distributed. Okay. Now, what you can do, load is, this is, suppose this is the center point C. Okay, and this is W per unit length. Okay, now what you have to do, you have to find a different points, right? You what yesterday I have explained in the a derivation when it is subjected to point load. I've considered two section. First, I considered the portion AC and I considered the section here. Then I considered the portion CB and considered the section here. But what you can do, no, you can do in other way also. In only one section also you can consider, not a problem. So today I will do according to that. Okay, which is comfortable for you, you use that principle. Okay, now what I will do, I will consider the this one, what you say, this section is here. Okay, I will consider section here. Okay, x. Okay, now which is at a distance of x from A, which is at a distance of x from A. Now what I have to calculate shear force at this value, right? Here we know that shear force at any section x at a distance x from A, that is equal to RA minus WX. If suppose if you consider the section here, any side you can consider. If you suppose consider the section here, then what happens? What is shear force at x? That is RA into X. Suppose I will consider the section here. Any side you can consider. Okay. This is section. Okay. This is X. What is that now? Here reaction is there. RA. Okay. So RA into X. This is upward, left side upward, plus RA into X minus, here W is there, but you have to consider only this distance. W into X. Okay, RA into X minus W into X. Why minus? Because left side downward is negative. So if you consider from this side, RA into X minus W into X. Any side you can consider. Okay, then at different points you can find what is at A, what is at X and what is at C. Or you can consider from this side also. Section is here which is at a distance of X from B. Okay, now I will use this and I will find. Okay, this is RB. What is now shear force at X? Shear force at X is equal to, any side you can consider, not a problem. I consider from this right side. So this is right side upward, right? Right side upward is what? Minus RB. Then plus, this is acting, UDL is here. This is acting in the downward direction. So plus W into X. Right? This is shear force at X. You can, if you consider from this side, shear force at X is plus RA minus W into X. Any side you can consider. So I consider from this side. So what is that now? Shear force find at different points. Okay. At B, first point is at B. What is B? At B, X is equal to 0, right? So substitute here, X is equal to 0. What is RB? RB is equal to WL divided by 2. So minus WL divided by 2 plus W into this is 0. Okay. So if this whole term becomes 0. So at V, shear force is equal to, what is that? Minus WL divided by 2. Okay. Next, so this is, I'll write Fx. Okay. This is Fx is equal to minus WL divided by 2. Okay. Next, find at C. What is at C? At C, what is X? X is, sorry. At C, X is equal to L by 2, correct? L divided by 2. Substitute in this equation. What happens now? This is FC, okay? FC is equal to minus RB is there. That is WL divided by 2 plus W into what is X? X is equal to now L divided by 2. So it becomes minus WL divided by 2 plus WL divided by 2. So it becomes 0. At C, shear force is equal to 0. Next is what? At A. You can consider at A, that is X is equal to now L, correct? Suppose if it is at A, what is X? X is equal to L now, full length. Okay. Now, what is shear force at A? Substitute here. Minus RB, that is minus WL by 2 here, minus WL by 2 plus what is now at A, no? So here W plus W into now X is equal to full this one. What is X? X is equal to L now. Simplify this, what you get? This is WL divided by 2 plus WL divided by 2. Okay. So shear force at X is minus WL by 2. Shear force at C is equal to 0. And shear force at A is equal to plus WL divided by 2. Okay. Same thing you will get if you consider from A to B also. Suppose section is here. What? If you get in terms of RA first. So RA into X, then you have to substitute at different points. At A it is 0, X is equal to 0. At C, X is equal to L by 2. And at B, X is equal to full length L. Same thing you will get. Okay. Any side you can use which is comfortable for you. Okay. Now what and same thing is written here. We can see that shear force at A is equal to RA 0.5 WL, where X is equal to 0 and decreases uniformly by a straight line to 0 at the midpoint of the beam. Okay, beyond which it continues to decrease uniformly to minus 0.5 WL at B as shown in the figure. Okay, how it is like this. See here, this is beam of simply supported subjected to UDL. Okay. At A, it is plus 0.5, right? Here, at A, it is plus 0.5. So, above the line, this is the baseline. So, 0.5 WL. Then, at C is equal to 0. Then, again, at B, it is minus 0.5 WL. Therefore, it is minus. Okay. Then, draw the line here. This is a straight line. This is SFT. Okay. Like this you can find SFT values and draw shear force diagram. Okay. Next we will discuss in the next class how to draw bending moment diagram. Hope all of you understood. If you have any difficulty, we'll discuss in the class. Okay. Thank you.